My name is Milad Soltanalipour. I'm a doctoral student at the Polytechnic University of Catalonia, and I will be presenting a study on the ductility of open rib and reentrant composite slabs. The layout of this presentation is the following. We begin with a brief introduction, describe the design method in the code, and then the objective. We will have a brief look at the studied specimens and describe experimental results, and will analyze them. The finite element approach and its findings come at the end, and finally we summarize the presentation with the most important conclusions. Composite slabs are well-known structural elements used as flooring systems. The profiled steel sheeting exists in different cross-section shapes. It can be open rib, with or without a top rib, reentrant, or closed rib. In this study, the slab cross-section behavior is analyzed using a finite element approach and compared to the experimental results. Conventional slabs in the construction are used for this study, and they consist of the profiled steel and concrete, without end anchorages and no reinforcements neither at the top nor at the bottom. This is the same way that the slabs should be tested to evaluate their shear resistance according to the standards. A method to evaluate the design resistance of the composite slabs is called the partial connection method. We will skip over the details, as the objective is not to explain the theory, but the question is, does the common types of slabs, open rib and reentrant, show a stress distribution close enough to the partial connection hypothesis or not? And if they behave differently, what are the reasons for that? Let's start with a brief look at the studied specimens. 16 tests, including 12 open rib and 4 reentrant slabs, are used. They consist of short and long spans, which were cast fully supported and tested according to the requirements defined in the code. All specimens failed by longitudinal shear and in a ductile manner, as defined in Eurocode 4. It should be highlighted that ductility is an important criterion because it defines whether the partial connection method can be used or not. As the experimental results show, after the recorded end slip of 0.1 mm, the load increases by more than 10%, which is the condition for classifying them as ductile. Now let's see how much the end slip is developed where the load drops. Open rib slabs usually have a descending force-slip relationship after the peak force, and the slip at the maximum load ranges between 2 to 5 mm. But in reentrant slabs, the curve is horizontal, and they can exhibit a greater end slip value, which reached up to 10 mm in the studied cases. The end slip limit in open rib slabs is related to their embossment design. The concrete slab is not continuously clamped by the geometry of the profile, as in the reentrant shape, but the embossments are providing a discontinuous reentrant angle and defining when the vertical detachment occurs. Once the slip begins, after a certain value, the concrete slab is free to detach. Although the space and depth of embossments can be slightly different in each case, the force-slip curve usually starts to descend after the slip geometrical limits. Let's have a second look at the assumptions of the partial connection method. The slip can be developed without vertical detachment until the steel yields in tension and compression and concrete in compression. According to this assumption, the stresses are beyond the yield limits at the maximum resisted force. We've studied the very same composite slabs using a finite element analysis. First, let's have a look at the modeling approach. The steel mechanical properties are defined using an elastic perfectly plastic stress-strain relationship. The concrete behavior is linear with a brittle failure to represent cracking. Tensile stress relaxation is also included to improve numerical stability. To address the slip dependency on the embossment design, the embossments are defined wherever they exist, on the webs or flanges. Therefore, the interface of materials consists of three-dimensional contact elements with complex geometry. To allow the contact elements to slide and detach with no restriction, standard unilateral contact behavior is selected. The coefficient of friction is 0.5 in the case of galvanized steel and 0.1 for stainless steel. Due to the symmetry conditions, only a single half-rib of the slab is modeled. The slip development is assumed to be symmetric on both sides of the span, and the border effect of the ribs is assumed to be negligible as done by the standards. The crack inducers are created as a plane discontinuity of nodes below the load line and with a depth greater than the profiled steel sheeting. This is the same way that is applied in the experimental tests. Crack inducers are used to perfectly define the shear lengths to ease the calculations of longitudinal shear strength. Finally, the support is defined as a constrained vertical displacement and the load is applied as a displacement increment. The results show a satisfactory verification in terms of ultimate load and force midspan deflection curves. Now let's see the cross-section stress distributions. This is the von Mises stress distribution and the maximum resisted force stage on the steel. The plastic stresses, shown as red contours, are developed usually below the neutral axis. In these zones, the slabs with a reentrant shape show wider yield zones compared to open rib. This is the stress profile corresponding to the critical section. The neutral axes of the concrete and steel are relatively closer to each other in reentrant slabs. It shows that the composite action is well developed. It also shows that the plane cross-section hypothesis can be considered valid, since the two neutral axes approach the homogeneous neutral axis of the cross-section. On the opposite, the neutral axes are far in open rib slabs, which shows a lower composite action. In this slide, we see the distribution of the third principal stresses in the concrete. The fact that the stresses are far from the compressive strengths is not surprising, and several experimental researchers have concluded that. The shape of the stress profile is similar in all cases. It is a triangle at the upper fibers and follows a straight line below the neutral axis. Let's summarize the findings. Slabs are classified as ductile, and the use of the partial connection method is allowed. The hypothesis of yielding cross-section, as stated by the partial connection method, is assessed. Finite element results show that the stress distributions assumed by the standard cannot be accomplished in open rib slabs. After the vertical detachment occurs, the load drops, and the stresses are still below the yield point. The assumption can be assumed with reentrant slabs, where a wide zone of the steel profile is under tension. The concrete slab is clamped by the profile, and the stresses can grow until the total yielding of the cross-section. The slip extension has a geometrical limit in open rib slabs, at which the vertical detachment occurs and the load starts to decrease before yielding material. Based on the findings of this study that are limited to the number of the studied specimens, the recommendation is to assess the possibility of redefinition of ductility in the standard. Currently, ductility is regardless of the total slip extension and the slip at the maximum load. It is also independent of the shape of the profile steel. Thank you very much for your attention.